Hi there. Today we'll look at Rethinking the Truly Unsupervised Image-to-Image Translation by Kyung-June Baek, Yoon-Jae Choi, Young-Jung Oh, Ja-Jun Yu, and Hyun-Jung Shim. So in this paper, we'll deal with image-to-image translation in an unsupervised fashion. So on a high level, they replace the need for domain or really single image label annotations in image-to-image translation by training a guiding network that is able to sort of do a self-clustering of the image domain. And therefore, that guides the image-to-image translation instead of the previously needed labels. I myself don't know too much about image-to-image translation and style transfer and all of this stuff. This has always been kind of a mystery to me, and will try to make as much sense as possible out of this paper if you're with me. I might not get everything right, but I will give my best, of course. As always, if you like content like this, consider sharing it out and leaving a like and a comment. I do read the comments, so I get a good idea of what you have to say about it. Cool, so what we're seeing here is an example of image-to-image translation of like a sort of a style transfer. Now, what you'll have on the left is a source image. Now, the goal is to translate this source image to a different domain while sort of keeping the features of the image the same. And here is sort of, I'm always confused because here it's like we keep the pose of the cat the same. Okay, so we sort of keep the same cat, but we want to change its style, which means its breed in this particular case. So on the top, you can see that the domain images they come in these different groups. And in fact, it's not only those four, but the entire dataset is split into these different groups. And among these different groups, you have some sort of a shared style. Now, this shared style is what you would like to transfer to the source image. So if you transfer the style of all of these cats right here, which all seem to be sort of ginger cats, to this instance right here, what you'll end up with is a cat. Okay, it was ginger before. Might not be the best example, but you sort of get what I mean, is that the thing that you transfer is whatever is common among these domain images, okay? And that's what I guess explains why the pose of the cat stays the same, because it is basically taught to keep the image the same, except to transfer whatever's common among the images in the domain class. And that's image-to-image transfer or translation. Now, until this paper, at least that's what the paper claims, these image-to-image translation models, they required labels. And why is that? That's because you need to know how to build these domains here at the top to get these different style vectors out. Or you actually would need label annotations for each image, for each single image. You would need to know which one of the source corresponds to which one of the target. So they have a graphic right here where they explain the sort of different stages that image-to-image translation went through historically. So first, you'd have to have corresponding images one-to-one, where you'd say, okay, here is an example of a sketch of a shoe, and here is the corresponding shoe. Here is the sketch of another shoe, and here is the corresponding shoe, and so on. And from that, you could learn a model that translates from one domain to the other, because you have corresponding image level annotations, which image corresponds to which, so basically which element of the domain A corresponds to which element in the domain B. Then the next stage of this was when you only need set level annotations, and that's sort of what we looked at if you had supervised labels for domains. So what you'll say is that there are three domains, A, B, and C. And actually, let's forget C for a moment and just deal with A and B to make it equivalent to the thing on the left. Now I just know that these things are instances of class A and these things are instances of class B. Yet I don't there's no correspondence, right? There is no this corresponds to this or something like this. So image-to-image translation is now possible between domains when I just have domain level labels. But this is still expensive. Collecting these labels, is like collecting labels for a supervised dataset. A human needs to look at each image and then conclude what sort of domain it is. Their paper introduces the following, where you do not have domains anymore. You simply have a dataset X. Now, this dataset, your hypothesis is that there are still going to be domains in the dataset. I guess they can be overlapping or not, but there are still going to be domains. You just don't know what they are. So in this case, I guess you could differentiate these people into many, many different ways, but in essence, you're going to assume that there is some kind of a domain structure. You just don't know what it is. But if you knew what it was, then you could simply apply methods from here to the data set and you'd be done. Now, their paper shows that if you apply something like a self-clustering approach, and we've seen these approaches before in the paper about learning to classify images without labels. If you have techniques like this, you can do like a self-clustering approach on this dataset X right here, and then you could learn your image-to-image translation. Yet this paper shows that if you do that, the quality is not as good as if you do both things jointly. So what this paper does is it jointly learns to cluster, let's say, to self-label the images and to do this image-to-image translation. And by doing the tasks jointly, they help each other perform better, okay? That's the general overview. So how do they do this? They have 3 different parts to their model. There is the encoder, or they call this the guiding network. There is the generator, and there is the discriminator. So the generator and the discriminator, they are fairly standard GAN generators and discriminators, so general adversarial network. But they have like a bit of some sort of twists. So you can already see from the drawings right here, the discriminator is probably the easiest. The discriminator gets an image right here. It doesn't have to be a generated. It is either a generated image or a real image. And it needs to decide, you can see right here, this means that the input domain is a vector or an image in this case, and the output is a number. It needs to decide if it's real or fake. Now, in fact, it's not as easy because you can see there are these multiple heads right here. So this whole thing, as I said, is built on this kind of pseudo-clustering approach. There is this pseudo-label that comes out of the left side. We're going to look at that in a second. But in essence, you assume that there are multiple classes, multiple domains in the data set. And the discriminator here has one classification head for each of those classes. So from somewhere outside, it will get the information, oh, this is now supposed to be one of those ginger cats, right? As opposed to one of those black and white cats or one of the brown-haired cats. No, it's one of the ginger cats. And then there is a special head on top of the classifier that only classifies fake from real ginger cats, okay? Which is a different classifier from the other domains. So the discriminator, it's sort of a conditional discriminator, conditioned on a label. Okay, from the discriminator's point of view, it's simply a label conditioned discriminator discriminating between real and false. And I think that's, how you train the discriminator is you would give an image and you would let this encoder here, this guiding network, label the image. And how we come up with this label again, that we'll look in a second. But this just gives the label, and then for that particular label, you'd classify the image into real or false. Now, the fact that there is this shared part right here, of course, is you could also think of having one discriminator per class, but the shared part gives you some shared features and so on, but it's not necessary. It's not the point is that there is a discriminator per class. It's class conditional. Okay. So what about the generator? I guess is the most complex. What about this encoding network right here? It's E for encoder, I guess, but they also call it the guiding network. So what this does is, what's this supposed to do is it'll take an image, any image, and it will output two things. One is a label and one is a style code. So the label is supposed to be a number between 0 and k minus 1. So that's supposed to be a class label. And how do you know how many classes there are if there are no labels? You just guess. And your best bet is to slightly over-guess. So if you expect there to be between 10 and 15 classes, maybe put k to 20. Okay, you don't want to under-guess, but you can over-guess. But not by too much, of course. So you have to have this estimation of how many classes, but then this E, it simply comes up with a class label, and it also comes up with the style code. Now, these two things are going to go then different pathways in this network. The label is directly going to the discriminator, right? The generator does not see the label. Okay. The style code does not go to the discriminator, but goes to the generator. All right, so the two inputs from the encoder, one goes to the discriminator, which is the label, and one goes to the generator, which is the style. Now, the generator, lastly, it takes a source image, and it takes this style code right here. Now, the style code is encapsulating, as we said, the style of the reference image. So the style is supposed to be whatever makes this domain of images the same. So the style, the way we're going to train this is that the style is going to describe somehow all the images that are from this label. The style is going to describe whatever the style is. It's very hard to explain. If we look at the loss, it becomes clearer why the things are how they are. So it takes the style code, and it takes the source image, and it combines them, and its task is to output this generated image. As you can see in this example, the generated image is basically this cat, but with the style of the reference image. And it outputs an image, and the discriminator, of course, then is tasked with differentiating whether that image is real or fake for the given label over here. Okay, so this is the entire thing, and you all train this jointly. So you jointly train the encoder to produce these class labels and the styles. You train the generator to take in the styles and the source images and output the generated image to fool the discriminator, and the discriminator at the same time is trained to differentiate between real and fake images based on the label that the encoder gives. Very, very convoluted and complicated, but there are a few things that make it easier. First of all, as you can see here, the pseudo-label is detached, is argmaxed and detached. So the pseudo-label really is a number, and there is no gradient backpropagation along this line. Okay, that makes it a lot easier. So what we first need is we need a way to train the encoder to come up with suitable class labels, even though it doesn't get any backpropagation signal into that part of its network. So that's where we start with the loss functions. The way we're going to do this is we're going to take the following approach. We're going to take an image, and we're going to take a randomly augmented version. So, for example, a random crop or a horizontal flip and so on. So now we bring in ideas from self-supervision. And again, if you watch the video on learning to classify images without labels, this is one of their main staples, these self-supervised approaches. really tend to learn representations that allow you to self-cluster. Now, in that paper, they go further and they do this nearest neighbor thing. In this paper, they just do sort of the first step of this self-clustering, which I guess makes it such that you could potentially improve this paper by applying the other paper, but who knows? So we're going to take an image and we're going to augment it. Okay, so that means we're going to like random crop it or change its luminance or whatnot. So we have two versions of the same image, and what we want to maximize, the mutual information between, not between the images themselves, but P is going to be this output of the encoder. So X goes into the encoder, and the encoder outputs the style and the class label. And the class label here, so P is going to be the class distribution. All right, so this is going to be like a histogram, or maybe the logits, so it's going to be a histogram over classes from which we're going to sample the label C or L or whatnot, Y hat, Y. But the P is the distribution over output classes. So since we don't have a label, we can't train the distribution like in a supervised way. So what we'll have to say is we want to maximize the mutual information between the output distribution of the image and the output distribution of the augmented image. Now that entails the following two quantities. There's the entropy of P, and there's the conditional entropy of P given P augmented. Now, first of all, it means we want to maximize this, the entropy of P. And that's supposed to be over the entire data set. So this is the entropy over the entire data set X. What it means is that we want different X's, so if there's X1, X2, X3, and so on, we want those to have different distributions in labels, okay? So if the entropy is really high of the distribution P, that means that different images get assigned to different classes. Something like this, all right? If this is low, then that would mean all the images basically get assigned to the same class, and that's not good. We want our classifier, since we don't have labels, it's basically a cluster. We want our cluster to sort of fill the space of possible clusters with the images. So that's the first thing. We want to maximize the mutual information. We need to maximize this entropy. And then second, since this is a minus here, we need to minimize the conditional entropy of P given P augmented. What does that mean? That means if we know the augmented version of an image, its class labeling should be the same as the unaugmented version. So that means that if I now take one of these x's to x1 augmented, then do a plus, augmented, right? Then that shouldn't really change its class label. And this is what these, so that should sort of keep the class labeling. This is horrible. But the idea here is that it's kind of a reverse thinking from supervised learning. In supervised learning, we have the label, like this is class 5, okay? This image is class 5. And our thinking is this augmentation techniques, if I random crop an image or if I change its colorization a little bit, the class is not going to change, right? An airplane in front of a blue sky is still an airplane in front of a bit bluer sky. So I assume that it'll still have the same label. Here, I don't have the label, but what I can require is to say, whatever you output for the image, it should be the same for the augmented image. So these two objectives are enough to give you sort of a rough clustering of the output space. Maximize the entropy, minimize the conditional entropy between two versions of the same image. Okay, that's how we train this pseudo-labeling approach. So now we have a model that can give a label to each image. Very cool. So how do we train the other parts? Now there are additional losses here. So I'm not sure. Yeah, we'll go over it. So this style part is also has to be trained, right? This encoder outputs a labeling. We got that covered. And it outputs a style part. Now the style part, if you can see from the graphic, it actually goes into, let me erase some of that stuff here. The style part actually is down here, and it feeds into the generator. And luckily they write detach here, and since they don't write detach anywhere here, that means that we do get gradient back propagation from the generator to the style code. So that means our encoder here is trained to help the generator with its task of fooling the discriminator. Okay, but first of all, we're going to forget about that for now. What we're going to do is simply look at a loss that they impose on the style. They don't have to impose that loss, but they have an additional loss on the style codes for the encoder, in addition to the fact that there is gradient backpropagating from G. So the second loss we're going to look at is this style loss. The style loss is almost the same. So the style loss is a contrastive loss. So what you want to do is, if you have your data set, you have your data set of images, and you take images out and you train your network on it, you take the next image, or you take batches of image, you train and so on, like this, right? And now you have this image. What you want to do for this to work is you want to build up sort of a queue of images that you have already looked at, like these images. These are going, and the queue can be, let's say 10 long, and you would always throw out the oldest and enqueue a newest. So when you're done with this image right here, you'll put it into the queue, you load your next image, and so on. So now, what does this mean? You now always have a queue of other images. And it's not important what they are, as long as they are others, right? Because now we're going to compare ourselves with others. And this is this contrastive loss right here. So the style loss is going to be a contrastive loss between this and this. Now the bottom part, this here, these are the others. These are the other images. And what are the individual quantities? So S is the style code of the image you're considering right now. S plus, you could have already guessed it, is the style code of the augmented image, right? So we had our image X. Let's go again with X1, X2, X3 are different images. So we put X1 through the encoder that gives us S, the style. It also gives us the class label, but now we care about this head that gives us the style code. And we augment X1 to be X1 plus. And we put that through the encoder that gives us S plus. And now we also put all of these other images. Remember, these are the images that we've looked at previously, but the only real importance is that they're other images. We put those through here, and they get the S minus I, in this case, 3 and 2. So now what we'll require is that the S, the style code of our image, is closer to the style code of its augmented version. So the same principle again. We'll say that, these augmentations, they don't really change anything about the style. Now this argument is a bit more wonky, but if you think of, random crops and random flips, don't really change anything about the fur color or so of a cat. So we want those two to be closer together than S is to any of these other images. Okay, so this is a contrastive loss where you pull together two things that you think should be close, and you push apart things that you think should be far away from each other. So this style loss basically guarantees that you have a distinct style for each image that is robust to the kind of transformations that you do under augmentation. Okay? Specifically, this style loss doesn't care about the domain, right? This is for each image. You don't know if these other images are from the same domain or from different domains. And that's why the style is basically individual to the image. But as we're going to see, the style does capture something of the domain as well. But this loss right here is supposed to be each image has a style, right? So this is the style code of X. This n+1 way classification enables E to utilize not only the similarity of the positive pair, but also the dissimilarity of the negative pairs, where the negative style codes are stored into a queue using previously sampled images. We observe that adding this objective significantly improves unsupervised classification accuracy in animal faces from this to that, compared to the previous overclustering approach. Okay, so we have two outputs now. And now we go to the adversarial loss. So the question is, how do we train the generator and the discriminator? So they have three different losses for the generator and the discriminator, and the most important one, of course, is this adversarial loss right here. So the discriminator simply tries to distinguish, is an image real or fake, conditioned on a class. So in case of a real image, and that's this line right here, it tries to distinguish, is this real or fake, based on Y, and Y is X fed to the encoder, and the encoder gives you a label. All right, and the label selects the head of the discriminator. At the same time that the discriminator is trying to distinguish real from fake, so these two lines, the generator is trying to fool the discriminator. So the upper, if you've never seen a GAN loss, the upper part here, that's the real data, and the bottom part here is the fake data. Now, at the same time, the discriminator is trying to distinguish real from fake, and the generator is trying to make the fool the discriminator. So both are of the generator and the discriminator are actually using that loss, but the sign in front of it is different. Okay, and since the generator is not involved in the top line, you can usually leave that away because there's no backprop path through that. And there's no backprop path here because we detach the graph right here. So there's no gradient signal going to the encoder. So this bottom line, what does it mean? The generator will take in an image and the style. Now S tilde comes from X tilde. It's X tilde going through the encoder, giving you S tilde. So this is the reference image. Right? This is, you want this style right here. This is the reference image, and X is the source image. So the generator is supposed to take the source image and basically apply the style from the reference image and generate X, I don't even know how to call this. X, not tilde, whatever, X fake, XF. And that's supposed to fool the discriminator. Now, the question is which discriminator, right? Because you need a label for the discriminator. The label is conditional. With this discriminator, it's pretty easy because it's simply the label of this image. Now, however, as you can see, the generator learns to translate X to the target domain while reflecting the style code S tilde. So Y tilde is going to be the label that comes out of this X. So this encoder right here is also going to give us Y tilde. And that's going to go here. All right. So recap. What we want to put into the discriminator is one time a real image like we do up here. And we get its label from the encoder. The encoder gets us a label for each image. Very cool. We'll also take the same image, put it through the generator, task the generator with transferring the style of another image from here onto it. We get the style from the encoder. And then the generator is supposed to make an image, and we feed that to the discriminator, and the discriminator discriminates, assuming it comes from class Y tilde. Now you see right here, the generator never has access to Y tilde. Okay, so the generator is kind of at a disadvantage here. The discriminator gets told what kind of image it is in terms of class. While the generator, because it needs to fool the discriminator, it needs to come up with an image of that class, but it has no idea of the class. It only has the style code. So it is forced to learn to map a style, to associate a style with a particular class. And that's how you get the domain into the style. That's why the style can capture something like fur color of the different cat breeds, because the generator is forced to take the style that the encoder gives and map it to an image of the class y tilde that also the encoder gives, but doesn't tell to the generator. Okay, and in fact, there is a more path, because you now backpropagate the loss to the encoder, which means that the encoder will even help the generator. It will help the generator make style codes that are very class specific. Now you can maybe think, why wouldn't you just have one output? Why doesn't the encoder simply output the label also as the style? Because that would be the easiest. And the reason is because we have different losses on the style and the label. Okay, otherwise that would be a valid tactic. So that's cool. That's the adversarial loss. That's the most important loss. Now there's also additional losses. So they do additional losses that they add on top for the generator. They say, in order to prevent degenerate situation where the generator ignores the style code and synthesizes a random image in the domain y, or in the domain y tilde, we impose a style contrastive loss to the generator. So now there's still the danger that the generator simply produces a valid image, right, from the data set, or even from the domain y tilde, though I don't know how it would know y tilde, or I've just not seen something. In my mind, it doesn't get the y tilde, but it could read it from the style. But here the danger is to ignore the style. I'm slightly confused by this part, but maybe looking at the loss will clear it out. So they say we impose a style contrastive loss to the generator. Now this is almost the same as we imposed on the encoder. So the generator, you can see there is a contrastive loss again, where you want these things to be close and you want these things to be far apart. So these S minuses, these are going to be the ones from the style codes of the images from your queue. So these are just going to be other images. Here, S tilde, that's going to be the style that you get from your reference image. So your reference image is going through the encoder, and that's going to give you this right here. Now, the question is, what is S prime here? Because before we simply had S, which was our source image style. Now, what is S prime here? S prime is going to be, it gets more complicated, yes. S prime is going to be, it's going to be the round trip to the encoder. So it's going to be, if I generate my image from the source image X and the style S tilde of the reference, and then I ask my encoder again, what style does this have? I get the S prime. So it's kind of a round trip, right? So I take this, I ask the encoder, what style is it? That's S tilde, right? Then I take S tilde, go to the generator together with a source image, X, and that gives me like X fake. And then I ask my generator again, what style would you assign to the fake image I just produced? And then the encoder will tell you, I'll give it S fake, or S prime in this case. And then I compare that S prime with the one I gave before. Okay, so it's sort of a round trip loss of my reference image. All right, so what does that do? if I now, and then I ask that S prime be close to S tilde. So that means if I generate an image with the style of my reference image, the outcoming image should better have the style of the reference image. That's all it says. So the style of the thing I generate, given this style, they should better be close, and especially closer together than the style with any other image in my queue. It makes sense, but it's kind of convoluted. So you go with your out, it's kind of a reconstruction loss, except in style space. All right, and then the last thing is an actual image reconstruction loss. So what you'll do is your generator will produce will produce an image from the source image and its own style. Right here, that's important. Before we input S tilde here. So this now is we input the source image and its own style. So we go with X, we go to the E, and we put the style here, and we tell the generator, if I input the source image and its own style, then what you give me back better be the source image itself, right? This is a consistency loss that tells the generator that basically it learns now. The generator learns to recognize an image with its own style, sort of, because it doesn't know, right? It doesn't know that what's coming in here is the style of the image X, but now you teach it. And I think before this loss, you'd have a good chance that the styles would just be all over the place. They would sort of be consistent, but they would not be aligned. And with this, you force that the style of an image itself, if you put that into the generator, it will lead to that image itself. Okay, that's it. So this is extremely convoluted, right? The discriminator is the easiest. The discriminator is a class conditional discriminator that gets the label from some mechanism that decides on a label, right? Okay, that's the easiest. The encoder has two parts: the pseudo-label, which is over here, which is trained completely unsupervised, detached from everything else in a self-clustering approach. While the style part here is trained, first of all, in a contrastive way, which makes sense, and also in a back-propagated way from the generator. So the style generation mechanism tries to help the generator, okay? And that means it's going to leak some information about the label into the style, because that helps the generator. The generator needs to, if the generator knows what sort of class it's going to produce, it's going to be better. Okay, so you can count on that information being in there. But also because of all the other losses that the generator has and the contrastive loss on the style code is going to sort of describe the individual style of an image, and but is also going to describe what the style of that class is, because it technically needs to contain information about the class. And that's why I think this works with the style, because there is no inherent notion of like this is the pose of a cat or something like this. It still seems like a bit magic to me. And then the generator is first of all trained to fool the discriminator, given a source image and a style. And you can fool the discriminator by producing an image that's so good, it looks real, and specifically it looks real in the class that the pseudo-label has given, right? So in the class that the encoder has given to it. So the generator must somehow come up with an image that's of that class. And so it will be forced to interpret the style code in terms of that class label, which makes the style code. And also, we have these two additional losses, which is the round trip loss to the style space. So whatever the generator outputs, you should be able to recover the style from it by putting it through the encoder again. And then lastly, there is a consistency loss where you say if I input an image into a source image and I input its own style, again, going through the encoder, you should give me back the source image itself. Very complex. And all of the generator loss is backpropagated through to the encoder. So this is the full loss. As I said, discriminator, easy, adversarial loss. Generator, adversarial loss, plus this style round-trip consistency, plus the own image round-trip consistency. Encoder gets all of the generator loss, all of it. So all of this goes here. So the encoder fully helps the generator. And it is also trained with this mutual information and the style contrastive loss. Wow, that's some losses. Wow, that's a lot of damage. So they do different investigations into their model here, and I don't even know if we've missed some of the pictures. But ultimately, what you can now do is you can do image-to-image translation either, and that's the cool thing, you can have a reference image for one, or what you can do is you can ask your discriminator what kind of domains are there. You can ask your encoder what kind of domains are there. You've guessed the number of domains, so it's maybe 10, or in this case it's 8 domains of cats, and you can simply divide your data set into these 8 domains, right? 1, 2, 3, 4, 5, and so on. No, this is 10. Okay, I can't see anymore. So 10 domains, and then you can simply calculate. For each image, you calculate the style vector. So the style, and then you simply take the average 1 over the number in that domain. You take the average style vector, and that's going to be your target style. So you can do image-to-image translation with a reference image, or you can do image-to-image translation for an entire group of images. For example, all the images in a given domain. And that's how they do these graphs right here. Now just quickly wait until my tablet decides to show me the paper again. Thank you. All right. They do a bunch of investigations into their holy, unholy mixture of losses. Especially the first concern is, couldn't we just train the guiding network like by its own, on its own, and then after that train this GAN thing, right? That's what we had at the very beginning. We said there's this guiding network and it does the clustering and all. Couldn't we just train this GAN architecture on top of the frozen guiding network? And their conclusion is no, if we train everything together, it works better. So on the left, you have whenever you train the guiding network by itself, and what you're seeing here is the t-SNE visualization. t-SNE is a nonlinear visualization tool of style codes extracted by our guiding network. The ground truth domains of all test images is represented in different colors. So this is a data set that has labels, but you don't provide the labels to this algorithm. The algorithm is completely unlabeled, but for purposes of investigating, we'll visualize the labels with colors. And what you'll see here are the t-SNE visualizations of the style codes. So things that are close together, they have similar style codes. And the ideal case would be if things that are close together here have the same label. And that means the style is sort of representative of the domain. Okay, and that's what we want. We want the style to capture the domain of an image, and ideally not the image itself too much. Now on the left, you see that there is quite a bit of overlap between these, quite a bit of wash between the style and the group. And on the right, if you jointly train the GAN together with the guiding network, you see that these classes of the style codes, which have no reason to cluster, are much more clustered and separated, and they are separated much more along the lines of the ground truth classes. Okay, so that's pretty cool. Now, I would actually be interested in what happens if you do the separate training with the full pipeline of this learning to classify images without labels thing and their nearest neighbor thing, because they've also shown that just purely this self-clustering doesn't work too well, but if you then do the nearest neighbor thing on top, then that improves the classification significantly. So this could potentially help either the separate or the joint training right here. And there might be a connection between the joint training and whatever they're doing. In any case, they also show that then these FID, which is a quality metric for GANs, lower is better, that the joint training goes way lower in the FID than the separate training. Okay, that's the reason why they built this convoluted thing, because it works way better. And here they ablate some of the losses to investigate what's really going on. And in this case, t-SNE visualization of the style space of our guiding network trained on this. Since this does not have ground truth domain labels, each data point is colored with the guiding network's prediction. So each color is whatever the guiding network says the class is, and the dot is one style. Each dot is one style vector, and they're projected down to 2 dimensions. You can see pretty clearly that the individual classes, the individual clusters of style vectors correspond to different labels of the guiding network, which is to be expected. But also, since they overestimate the number of classes in this case, you can see that even though the class label is different, the style network will group the very similar classes together. You can see here, these are both cheetahs, and here are both lions. So it'll group them together, which is pretty cool, and sort of verifies that it recognizes these different things, because you force the guiding network to make 10 classes, but the style network is simply continuous. So it's cool to see that the style network will make one cluster with styles, even though it's different labels. And here you can see different samples from these domains just to verify that the guiding network has actually learned to separate things. I still find this pretty magical too. This is completely unsupervised, and it sort of finds these clusters by itself. All right, they have a bunch of images here. As I said, this is no longer with one reference image. This is where you take the entire domain, so you self-label with your guiding network, and then you take the mean vector, and that's going to be your target style vector, and these are the source images that you transfer. And you can see that it works pretty well. So they always have like one adult animal and one child animal. I guess not, or just 2 different ones. Here, this is particularly cute, though I have to show you this fox right here. What's going on with that fox? Like, someone help that fox. Yeah. So we're not at perfection yet, as you can see, but it's, that looks like a pretty cool fox. Maybe. Okay, where did it go? Maybe it slipped. Maybe it's an offshoot of this one on the top left. Yeah, who knows? These data sets, they have their way. And so this is sort of where you can see the limitations right here. That's not how a baby snow leopard looks. You see the limitations here in that all of these animal faces, they're still pretty aligned, like they're fairly frontal, not exactly, but they're fairly frontal pictures. They're fairly standardized and so on. So I don't think we're yet at a level where we can just do, fully image to image. And you see it especially with faces, because we, as us humans, are extremely good at, seeing when there's something wrong with a face. But it's still pretty impressive what's possible. And I think if the past is of any indication, here is summer to winter. That actually looks good. If the past is of any indication, then this technology will be pushed pretty hard, and soon we'll be able to do this with a simple smartphone app or something like this. So I invite you to check out the paper right here. They have lots and lots and lots of examples and t-SNE plots and whatnot in their appendix. They have the code online as far as I have seen. And with that, let me know what you think in the comments. Bye bye.